Hi, everybody. Thanks for joining today's ELISA seminar, Functional Safety with Zephyr and Linux for Avionics, Automotive, and Industrial. We're very delighted to have Ayan Kumar Halder, who is the Senior Member of Technical Staff from AMD as one of the speakers, and Matthew Weber, who is the Associate Technical Fellow, Chief of Software Architect, Linux from Boeing, joining us as a co-speaker as well. So yeah, we're looking forward to having a great presentation and some engaging discussions. With that, I'm passing the microphone to Aaron and Matthew.
Hi everyone, my name is Ayan. I'm a senior member of technical staff at AMD and I'm driving the functional safety certification efforts within AMD as well as with the upstream community. I have been working on Zen for the past 4 years and I have been working on low-level embedded systems for a decade and a half. Um, so I would like to hand it over to Matt for introduction.
Uh, Matt Weber, as Min mentioned, I'm currently within a operating system team at Boeing as the chief software architect. I have a little over 19 years of experience in embedded. I started out doing embedded radios with Linux in real time, and today we're doing things related with safety certifying environments that can do mixed uh, types of safety workloads. And I've been collaborating with the Zen project now on this since point last year. And I think it's really interesting to see where you hope you'll see the overlaps, I think, between the two efforts that both of us are bringing together.
Thanks, Matt. So in terms of today's agenda, we will be introducing the Zen project and the Zen functional safety, and then we will be going through some of the key features which are used for the safety certification. And then the meat of the presentation is to talk about the safety certification artifacts, like where we are collaborating in the open source with Matt and with everyone else. Then we talk about the DO178C and how it complements the existing ISO 26262 and IEC 61508 standards in terms of our interpretation for the requirements and the testing. And then we will conclude this. So Zen project has been over for more than 2 decades and it maintains several open source softwares under its umbrella. And Zen hypervisor is one of the open source hypervisor that has been developed in the University of Cambridge in 2003. And then we have several key contributors to the Zen project, which include SUSE, AMD, EPAM, Renesas, Boeing, and many others. So in terms of industrial distribution, we have seen Zen being used in server, in cloud, in security, and in embedded system applications. Now, the Zen functional safety group was started probably like around 5 or 6 years back. So ever since the effort was started to port Zen on the ARM-based systems, since then it was realized that Zen could gain quite a lot of significance in safety critical systems. And we have quite a lot of contributors from the open source ecosystem who are contributing to the safety, to our safety efforts. And today I'll be presenting on behalf of the entire group. So there are a lot of engineers at AMD, at EPAM, and at other organizations, and also the community maintainers from ARM and from x86 who have been helping us to drive Zen towards safety critical applications. We do have meetings every other Tuesday at 4 p.m. CET time where we discuss and we try to brainstorm on how to move Zen towards safety certification goal. Now, the key vision that we have is to ensure that the safety certification efforts that we are driving for can be used for all the three standards, that is IEC 61508, ISO 26262, and DO178. And although the standards may require a bit of tailoring as part of the functional safety scope that each and every organization defines, there is a whole lot of common features set within Zen. And on top of those feature sets, we are trying to write artifacts like requirements, tests, and specification, which helps not only with the overall overall quality, overall testability of Zen, but it also shows how these features are validated and how they can be used in a safety environment. Now, if I step back a bit, um, Zen can be used like as a unified runtime manager. Now, on the left hand side, you would see that Zen is used more and more in a feature-rich environment. Like you have you have the infotainment systems which are using Zen heavily, and these systems rely a lot on the PV and vert IO. So this involves where there are devices that are shared between one or more VMs. And then towards the right hand side, you would see Zen being used more on the safety critical aspects, where you have each VM which has a very static configuration, and we want to use the minimal features in the Zen and in the VM so that the VM is able to do that specific task. In the last few years, we have gained a bit more momentum when we started our efforts to drive Zen for the Cortex R-based systems. And now we have a prototype of Zen that is running on the Cortex R-based systems. We have Zen running on the Cortex A-based systems, and we have the OpenAMP to do the communication. I will be talking more about the Cortex R and the MPU efforts in going forward. Now, in order to make sure that Zen is usable, we are trying to do this as a safety element out of context, which means that we try to define what all are the assumptions that Zen places on the surrounding components, firmware, bootloader, VMs. And we say that as long as these assumptions are met, Zen can be used in a safety critical environment. And this neatly complements with the effort that Matt has been trying to drive with the ELISA group, where we have like a safety context defined, and we are trying to see whether the assumptions that we are making can be turned into the requirements for the surrounding components, and whether and if we can have a open source safety system in place. Now, the key features of Zen, which makes it usable for safety certification. So the main feature that we want to talk about is Zen being a type 1 hypervisor. Type 1 hypervisor means that it can also be called like a bare metal hypervisor. It has a neat isolation from the operating system's VMs, which will run in a EL1 mode, and Zen will run in the EL2 mode. Now, there are specific set of drivers that Zen maintains. So Zen takes responsibility only of few devices like MMU, IMMU, UART, timer, and beyond that, it relies on the VMs to provide the additional functionality. Now, one key feature of Zen that was developed in the last few years, or I would say two key features. So one is the static partitioning. That is, at boot time, you define the resources that each and every VM needs. So there is no dynamic allocation or deallocation of resources. A particular VM can be assigned a device. We call that as the device assigned to a VM, and Zen ensures that that device is never assigned to any other VM. And then you could actually create all of these VMs right at the boot time. So traditionally, Zen used to boot the DOM 0, and then the DOM 0 would boot the additional domains. But in the safety critical, as we want that the domains should be booted in parallel because they have a static configuration that is defined. So we have now Zen who can start the control domain, the hardware domain, and the other domains in parallel. Also, with that, there has been effort going on to support Zen more and more on the ARM safety cores. So there is an effort that's going on to support Zen for the AE's Cortex A72 AE, GIG 600, and the MMU 600 AE cores. Now, the way we try to see Zen being used with Zephyr and with Linux is that Zen needs like a control domain. A control domain is like a domain which has some privileges, and it can perform some safety critical applications based on those privileges. Now, this particular domain has to be very small, very tiny, because this particular domain will be one of the domains that needs to be safety certifiable, as Zen would rely on this particular domain to do more and more of the platform-wide operations. And we could see that Zephyr is a good candidate to be to be in that domain. Then we have the hardware domain. So as we said that Zen trusts on the domains to maintain the hardware other than the key hardware peripherals which it controls. So the remaining of the hardware peripherals like the GPIO, the additional I2C, the GPU drivers, everything can be assigned is assigned by default to the hardware domain. And by that it means that the hardware domain is quite feature rich. It has to support many and many devices. Not only that, the hardware domain also has to support the key platform operations like platform shutdown, platform reboot, clock configurations, and these are the things which makes it difficult, or it makes it makes Linux suitable for it to perform like a hardware domain. Now, I do understand that there is effort that's going on also to make Linux as a safety certifiable domain, but maybe we'll get there in some time. And then we also have the other regular domains. So we have like a targetable domain and the untargetable domain. The key difference between the two is that the control domain, by default, it cannot be interfered by the other domains. The regular domain, it can be interfered in the sense that you could have a privileged domain which is trying to map the memory of another domain, and it can do so for various reasons, for PV, for VirtIO, for certain kind of VM to VM communications. Of course, you can also ensure that a VM is never able to communicate or is not meant to be communicated or interfered with other domains. And that's why we have introduced this targetable property, where we can say that the targetable is equal to no, and that VM becomes, in a way, suitable for running safety critical applications. So this is how we were trying to align the domain capabilities and the properties. The control domain, it can issue the shutdown, pause, unpause, suspend, resume. Now, one key thing here is that although the control domain can issue these functions, it has to rely on the hardware domain in order to perform the platform specific operations. And the control domain can also shut down, restart the other regular domains. So this means that there are certain key assumptions that we are making both on the control domain and on the hardware domain. The hardware domain, we make a key assumption that it should not perform any kind of suspend, resume, reboot operations without being first asked by the control domain to do so. So these are some of the key assumptions that we are placing on the VMs in order to run as a control, as a hardware, and as other thing, and as regular domains. So to continue with that, the control domain also has the tool stack. So if suppose there is a need to create and destroy the domains at runtime, the control domain has the possibility to do that. The hardware domain, as we know, that it is the default assignee for all the devices that is there. And the regular domain, it can be used either to have like a strict device assignment, or it can communicate with other domains using the PV VirtIO. Of course, the regular domain will have lower privileges compared to the control domain. Now, one key feature of Zen in order to provide isolation between the VMs is that it can isolate the very key resource that a VM needs, and this is the CPU resources. And here I would say that Zen supports multiple scheduler. It supports null scheduler, where you have the virtual CPU and the physical CPU which are tightly coupled or pinned with one another, which means that a VM, which when it is created, it is assigned a number of physical CPUs, and it will never ever be interfered by another VM for the CPU resources, because it will always run on those dedicated physical CPUs. You also have the credit to scheduler, where you would have, let's say, more VMs which can be context switched between the multiple physical CPUs. So the disadvantage of the null scheduler is that you are limited by the number of physical codes that you have. So you really cannot create many number of VMs. Whereas on the credit to scheduler, you can create, but then there is a certain amount of interference that you have to manage. And I'll take a pause here for Matt to explain about the ARINC 653 scheduler.
So the ARINC 653 scheduler was actually added quite some time ago to the Zen code base. It's in the upstream code base. And in an architecture that's using that scheduler, you have basically what's called a major frame schedule that occurs at the Zen level. and then you have like what's called like partition windows that occur at a periodic rate. So the diagram here just shows an example of how, say you have core 0, it's running a major schedule with a bunch of periodic processing, and within each of those partition or domains, you have your applications and your OS and your other content running. So it allows you to have a very methodical, predictable execution sequences, and then do that on each physical core.
So that's good. And now moving on from scheduler, we are, like as I was saying, that we are trying to add support for the Cortex R based systems. So one of the key difference from Cortex A based systems is that traditionally Zen has always been developed or used on the MMU based, memory management unit based systems. Now one of the key nuance of the memory management unit is that it relies on the page walks, it relies on the translation table walks, which means that there is a certain amount of, let's say, a time lag that can happen when a page gets translated. And you could basically map, unmap the pages on the fly, and you could have like a larger virtual address space. And so there is a certain amount of dynamicity that you get with the MMU. Now, in the safety critical world, we know that most of the time there is a constraint on the resources, and the resources are partitioned right at the boot time, which means that we already know how much of a memory a particular VM is going to use. And what Zen does is that it needs to just ensure that the VM is using only that amount of memory with the permissions that the VM is expected to do that. So in order for this, ARM has released the Cortex R-based systems, R for the real time, where it uses MPU, memory protection unit. And the memory protection unit defines, instead of page tables, it defines protection regions. There are a fixed set of protection regions. And using this protection region, you can do a static mapping between the virtual address and the physical address of the memory. So you would ensure that the entire memory is one-to-one mapped, and you could actually define the static configuration of the different systems. And here I would like to give a shout out to Zephyr and to QEMU. So when we started this work in 2022, we wanted to also see how would a VM run on such a hypervisor. And at that time, there were parallel efforts going in the Zephyr to support the Cortex R-based systems. So it was a perfect moment for us that we started this development together. The Zephyr support is already there; it's in place. In the Zen one is upstreaming in progress, and we have also now got the MPU support in the QEMU apart from the ARM MVP. So you have the ARM fixed virtual platform, and you also have the QEMU to run the ARM V8R based systems. The other key feature is the MISRA C adoption. So we have adopted quite many rules in the Zen project. So there has been around 120 rules that has been adopted. And we now have like a Eclair-based MISRA C scanner in the upstream CI. So each and every patch that is sent out, we ensure that the patch doesn't introduce any regressions. And this work has been going on for the last several years, and we had several contributors who have been helping us in order to sanitize Zen. So we have got quite a lot of fixes that have gone in. So now to talk about the key safety certification artifacts, will be the main artifacts where we are collaborating are the requirements, the architecture specifications, the trace, and the tests and the traceability report. So this is like the entire flow that is in front of us. It shows the entire traceability from the market requirement, product, SSR, to the test cases, all the way to the test jobs. And a shout out here to the Open Fast Trace folks, Sebastian and Christopher, who had started this project called as Open Fast Trace. And they have been maintaining this for the last 5 years. And it's a very lightweight requirement tracing tool that we have used, and we found that it's useful. It helps us to maintain the requirements as code. Now, starting from the market requirement. So everything is defined by what is the scope of your functional safety certification. And that is where we define the market requirement, where we say that what all are the requirements that Zen or any hypervisor is expected to fulfill. So the market requirements are written at a very high level. They give a high level view of the system. These requirements are then translated into one or more product level requirements. So you have like in case of run, if the requirement is running Zen on ARM and x86 VMs, what it needs is that Zen needs to provide an emulated timer and an emulated UART, apart from many other things. But just to take an example, so these product requirements are written with a Zen's architect's point of view, that what is it that Zen should provide in order to run those VMs. Now, if we drill it further down, then we see that okay, from the architect, then what is the subsystem owner's perspective, which means that in order for Zen to provide a emulated timer to the VMs, what is it that Zen is actually doing or providing? So Zen is probing the generic device tree node, it is reading the system timer frequency, it is providing access to certain registers to the VMs. And the way we have written each and every requirement is that the requirements are in plain English. We are trying to follow the NASA format, and the requirements should be testable, and they should be testable independently. Most of the requirements are written from a black box perspective, which means that the requirements actually define the expectations that a domain has from Zen, because Zen is one single binary, and the way it will be used in deployment is with that binary, and it'll be used from the domains. So we are trying to define that what all are the features or interfaces that Zen provides to the VMs, and how it can be tested in the most granular way. Now, with this in mind, we have tried to have a good organization of the requirements. So we have the domain creation, the domain fully emulated, partially emulated, and we have also some of the requirements for the Zen internals, like for the booting, for the firmware, which defines that what Zen does during the booting and the firmware time. If there is a time, then I will show you our repo, and I'll show you that how we have organized our requirements. And this entire organization is out there under the Zen Fusa workspace group. Now, as part of the requirements, we have to also define the assumption of use. Now, there are certain things that Zen relies upon, and it means that so Zen places certain assumptions on the external components. As an example, the firmware is expected to program a particular register, CNT FRQ register, with the system timer frequency, because Zen cannot validate the correctness of this register, the correctness of the system timer frequency. It will just use what value it is. So in order to define such kind of assumptions, which Zen cannot, Zen has very limited or no means of validation. It has to just trust. So that's the reason we have defined a set of AOUs, and we have defined AOUs for everything, for the hardware, firmware, bootloader, domains, and the compiler. And certainly, even on the VMs as well, like in order to run a safety critical VM or in order to run a QM VM, we have defined certain assumptions. So in order to run as a safety critical VM, it should mask the event channel notifications. So event channel is a means of communicating between the different VMs, and Zen has a way to block or unblock the event channel notifications. It can only block it if the domain requests it to be blocked. So any domain which is performing any critical task, it needs to ensure that it has masked the event channel notifications. And in order for a VM to run as a hardware domain or a QM domain, it needs to support multiple platform devices, because it has to perform the platform specific operations. Now, one key thing that we found out was that all of these requirements have to be traced down to the code, because ultimately we are trying to test the code, how it is going to be used in deployment. And a key challenge is it's very difficult to put markers in a code that is upstream, open source, and constantly under flux. It's under change. So what we have done is we have defined the design of the code in the architecture specification. The architecture specification explains how those requirements are fulfilled by the code. And there is a way by which the architecture specifications are linked to the source code. So in a way, you can look at the architecture specification, and from the linkage of the arc to the source code, you do know what part of the source code implements this particular design. And there are also linkages between the SSR and the architecture specifications. So by doing this, we are trying to avoid putting any markers in the code, as well as we are also trying to define more and more nuances in the architecture specs. As an example, our requirement talks about the positive aspects. The negative aspect, that is when Zen is expected to fault, when Zen is expected to return an error, when Zen is expected to throw a timeout, or what are the hardware software interfaces within Zen. All of these internals are explained via the architecture specifications. And in order to verify all of these, we have the different kind of tests. So starting with the domain based tests are, let's say, the tier 1 category of tests, because this is actually testing how Zen is getting deployed. Zen in deployment will be used by the domain. So the domain based test will test like the actual usage of Zen, and all of the requirements are mostly covered by the domain based testing. Now, besides that, you also have the fault injection tests. Let me take a pause if anyone has a question. Oh, okay. So you also have the fault injection tests. So fault injection tests defines that if a domain is expected to send a certain parameter range as part of its hypercall, what happens if the domain is sending the unexpected parameters, the parameters out of range, or it is trying to do something that is illegal, that is, it is trying to access the memory that it doesn't belong to it. So these are the kind of fault injections that we have defined. There are also fault injections that are based on the hardware, like the hardware is triggering a fault at certain point. Then you have the fuzzing tests, you have the runtime tests, and you have the internal interfaces tests as well. Now, the domain-based tests. Now, one of the key thing about the domain-based test is it tests quite a lot of code together, because it is actually testing Zen from outside. So it can be seen that in some of the cases, we do need some kind of, let's say, more granular tests, and that is where for some for the hardware drivers which are in Zen, we have defined like a test mode within Zen itself. So we have defined stubs within Zen by which you can do unit testing of the Zen's hardware drivers, and you can actually test, for example, the gig v3 SGI SPI interrupt capability within Zen. Of course, then the disadvantage of these tests are that these tests lie with the code of Zen. They are encapsulated using a config, but still they are within the code base of Zen. So they can be a bit more, let's say, hard to maintain. Now you have this internal interface test. So one of the very nice way to test some of these internal interfaces, internal data structures is using GDB, because with GDB you can take a pause and you can actually inspect what all are the registers, what all are the values of certain parameters. You could also state, like, what happens if certain parameters are being changed between the interfaces. So for example, you have the scheduler subsystem, you have the credit to scheduler. Using the GDB based test, you can actually mock what happens if the credit to scheduler fails initialization. What is its impact? So these are the finer tests within Zen, which are very difficult to be triggered from the domain-based tests. And this is where the GDB tests comes into picture, where you can also use GDB to inspect the return values, and you can simulate the different failures. So thanks to Dimitro for coming up with this idea. It's really good. And then you have the hardware fault injection tests. So the hardware fault injection tests are like, because we use QEMU, so QEMU is quite configurable. Like, we can write tests within QEMU, which can be triggered at certain point in time. For example, Zen is booting the domains. What happens if there is a S error received at that point in time? These kind of things, which are very, very difficult to simulate on the actual hardware, we can use the QEMU for that, and it is quite powerful, as we have found out. And then we also described about the software fault injection or the negative tests. That is, if the domain is sending some parameters that is out of range, then can Zen return an error? And similarly, because Zen is also has an interface with the device tree, so we also try to check that what happens if someone has provided an incorrect configuration of the device tree. Of course, like, if there is a certain incorrect configuration, like this, like the system counter, like the frequency register. In that case, it has to belong in the AOU. If suppose there is a way for Zen to detect it, then of course, like we could say that okay, Zen detects it, so maybe it is possible for Zen to say that okay, this particular value is not supported, and it can stop the booting right in the initial stage itself. And last but not the least, all of these tests, while they are testing certain features in isolation, certain certain interfaces, etc., you also need to run the tests on Zen in the actual deployment scenario, which means that now you have Zen, you have multiple domains, you have domains doing n number of operations, and you do want to see whether Zen is able to stay alive with the domains. Now, here specifically, we are tracking the memory allocation. We are trying to see if Zen has exhausted the memory while running the different domains. Now, now, in order for us to make the claim that Zen relies very less on the runtime memory usage, and anytime there is a allocation, there is also a corresponding free that is given. So Zen would need to, we would need to instrument each and every allocation that happens at runtime, and then we have to show that okay, there is a corresponding free that's going on, in order to prove that there cannot be a situation where Zen is going to run out of memory, because that would be like it would be like a major catastrophe, that if Zen is running out of memory. So we are using tests also to instrument that level. And then we have the fuzzing tests to fuzz some of the interfaces. Now, after all of these tests, there is still, let's say, a missing puzzle. And the missing puzzle is this, that anyone who wants to use Zen in a safety critical system, they often talk about the space and time partitioning. Now, while we can use the domain-based tests, some of the internal interfaces tests to prove that, we do need, let's say, tests which can actually test the way Zen is setting up the page tables, the MMU configuration, the stage two stage two page tables. And this is where we feel that the mechanism that Boeing has put in place is able to achieve that, because MMU P2M, this is, let's say, the most safety critical part of Zen, which is providing that address space isolation. So we are trying to have more and more redundant or rigorous testing for these internal features of Zen, and that's a key thing that Matt will talk in the upcoming sessions. And then we are trying to define like a safety use case for Zen. So what happens, how do we define a real in context? Like what's the safety hardware? What's the safety trusted firmware? What are the safe VMs, etc. to define a proper safe context? And this is an excellent work that ELISA is doing in order to define this open source safety use case. So with that, I would hand over to Matt. Sorry if I've gone a bit over time. Over to you.
No, this is great. Starting off with a table that you're able to pull up if you'd like using the QR code, the safety standard space is really interesting because it all really started back with industrial standards originally, and then different industries built on that. There is I think, flip in numbering and letters that, just to get that clear from the start, you'll see DO-178. The lowest level is a level E, which would be like your QM. They're in the middle, circled in green. And your highest level is design assurance level A. And at level A, your failure rate is actually lower than what your automotive is even aiming for. Your ASIL D is really more of a Dow Bravo, or sort of right in between. And what that influences is the amount of life cycle activities, the artifacts you make, the reviews, and the things you go through to have that human involvement to drive the chance of failure out of the final solution. So this decoder, I think it's interesting to look at the problem of when you have Zen. If you can take Zen to have the lowest failure rate possible, the better. That's where we want to be. It's going to give us other opportunities. So next slide. So just a little bit touch on DO 178. It is a standard for certifying software. And on the left in the top there, you'll see design assurance level is how we refer to levels from a system perspective. And there's ARP standards that govern how civil aviation does system certification. And then right below that is software level. So within DO 178, C software level or A through D is how we reference it. It's equivalent to DAO, but at least when we're talking software, it's SWL. And you'll see the life cycle artifacts there on the left. It's a lot of the same stuff that Ayan shared with automotive. And I think the really interesting opportunity with working together on this is there's a lot of overlap, and there's areas that I'll mention in a minute where we actually probably complement the automotive effort. We may simplify some of the cert because of the extra what we call rigor, or, extra uh, activities and objectives. And on the right, I give you an example of what that means. So objectives are basically a list of things in that table that you need to achieve, and then it's appropriate to certain levels, and then you have certain outputs. And the activity column there is basically like there's things you need to do in addition to producing those outputs to be able to claim that you've done that. And if you're curious about more detail on this, there's a QR code in the upper corner there. There was a seminar done in the past years that really goes into this much deeper. Next slide. So, as I hinted earlier, that top section on failure rate, DO 178 level A is one level lower than ASIL D. And what that means from our side is looking at low level requirements that completely cover all code behavior. And the challenge obviously is a lot of the code exists, and that's a whole other talk. But you have low level requirements capturing all that. The goal is to actually map those to like design requirements on the automotive side, plus code, and then actually do unit testing with mocking. And what that means is we take all that code, basically, you take it out of Zen, you white box test all around it, and then you build your test tables to do complete coverage, all scenarios. So we're talking absolute coverage of all intended behavior. And that's what the equivalence class tries to do, groupings of tests to make it more scalable. And then boundary is what it is, right? With functions, you're trying to capture the extremes. But the concept that we brought to Zen is basically looking at this white box unit testing where you pull pieces out, you use a mocking framework with a tool called Ceedling that allows you to take those most critical parts of Zen and do that requirements-based test of complete coverage. And if you're familiar with like MCDC coverage tooling and testing, you would then take that tooling and basically do analysis on these unit tests to show you've completely tested the system behavior as expected. So that's one area where I think we'll bring extra rigor. We also I think we have independence, and there's other aspects of how we do the work that will come into play. But I think that's less of a thing than the testing and bringing the LLRs. Other two areas I just wanted to mention, we talked about a bunch of lifecycle stuff in the prior slides, but that was a lot of context. And I think the one thing that we're trying to bring is the aviation space has done a ton of work standardizing computing, whether it's the I/O interfaces or whether it's the actual API that software integrates against, which is ARINC 653 is the standard that specified that. And I gave a QR code there that'll get you to the ARINC Wikipedia page. And there's actually on the 653 page, there's a really good ARINC 653 hypervisor paper that I dropped a link to the chat earlier for another question about it. But that actually sort of was the vision for what you're seeing come together today. And it's sort of bringing that environment that the standards spec and doing it with Zen. And then the other standard that's really important is when you have a system like that that has a bunch of mixed safety levels, organizing and managing that is a very large task. And the integrated modular avionics lays out the stakeholders involved, the activities that are going on, and then how you bring the system together. So it isn't really software specific. But the fact that those standards all exist gives us a framework to basically take the functional safety work that Zen's doing, put it within context of an aviation system, and then work out the details of how it'll actually come together. Last bullet, it's all software development, life cycle activities that we're doing. The tools overlap, the way we qualify and document tools overlap. I think that would be probably a huge thing, just because you always want to update tools, and you're usually burdened by the fact that, well, this is being used for cert, I can't update it. But if you're collaborating, maybe there's more opportunity. Next slide. So just to tease the June workshop, the QR code's in the upper corner. You can get an invite. And what we're going to be bringing up there is looking at, here's a deployment of how I could go build a system from a DO-178 perspective, where I am taking Zen to level A cert, and I'm providing guarantees that are a slight level above where ASIL D is aiming. And the pull requests at the bottom, we're working through ideas and stuff, still developing the talk. If you're curious about the background, this diagram's out there, some slide work we're doing, but we wanted to start talking about what are the key pieces, where are we a subset of the automotive work, where we may be driving more rigor and activities into the automotive work. And you'll see some of that in the June talk. So with that, I'll hand it back to Ayan.
Hey, thanks, Matt.
Yep.
So with all the features and the work set that Matt defined, the next important challenge that is coming in front of us is that how do we keep all this safety certification evergreen? And there would be some discussions that we would be doing in the June workshop and also at the Zen Summit. We want to make sure that there is all of these requirements, the architecture specifications, the tests, they are kept up to date with the code. And for that, we want to, let's say, onboard new maintainers who would be looking at these artifacts more from the functional safety aspects and ensure that this is kept up to date on top of the changing code, while at the same time not overburdening the existing developers, existing maintainers who will be focused more on the code itself. This is again like a open challenge in front of us, and we have to see how to get it through. And then last but not the least, the bigger goal in front of all of us is to define like an open source functional safety ecosystem. So we have Zen, we have Zephyr, we have Linux, who are all trying to work together towards that open source functional safety ecosystem. And it can only happen that if we collaborate and if we walk together, because there are certain assumptions that one component will place on the other component. And if we can take all the best practices that the open source community has developed in their respective projects over the years, and we back our safety certification efforts on top of that, while keeping it as much as possible open and transparent, and in order for people to find issues and fix them, we would require all of you to come to help us, to join us at the with this at and in the mailing list, to join us on the matrix channel, on our calls, and see how we can do all of these things together. Because functional safety is not just like a one time done and dusted thing. It needs to be kept up to date with new features, with the code changes, and with all the new kind of bugs or new kind of design challenges that we will uncover, similar to the security issues. So we have to keep it together, and we have to keep it going together for the functional safety ecosystem. And that's going to help the automotive, the space, and the many other ecosystems here. So with that, I would like to take any questions if you have.
I guess, Ayan, if they have questions about getting engaged in the functional safety calls, what's the first step for that? Should they register with the mailing list and just send a note, or should they reach out to you?
I would say the first step is please register on the mailing list, because all of these discussions, we want to keep it on the mailing list where we discuss the code and the other things. And then do send an invite. You have to join the matrix channel, and you have to you have to have like a matrix username, and once you have that, then you can send me and I can add you to the channel. So I can point you, like if you can send me an email or something, then I can point you to some of the resources. And the other thing would also help, that if you could give like an introduction and give a brief thing, like where your interest is coming from, because we also want to complement each other's expertise and efforts. So yeah.
I'll drop a link to the list in the chat for anyone that's interested.
Yeah. Also, if I can show you, so this is like a workspace that we have defined. After this call, you are free to go and have a look at this. And we have the requirements, we have some of the test specifications, we have the architecture specifications here. This is like a staging repo for all of us, and we are trying to get it in zen.git in the upstream. So this is where we try to collaborate in the open, and we try to move things forward, because all of this requires a certain amount of pre-work that's to be done in order to show the benefit to the community. Yeah, I'll go back to the slide. Yes.
David,
Any
the London link is above in the chat. If you're able to see it, I'll grab it here as well and post it again.
David, I think your question is ideally, if you can attend in person, that's probably the best way to collaborate and network with people who will be there. But we will accommodate remote participation as well. So the schedule and the registration is in that link that Matthew just posted. There are a lot of questions in the chat. Matt, do you feel they're all addressed or not?
I think we've addressed them. I guess if anyone feels we haven't, post again if you could. I do want to make a plug for a post that I made a few minutes ago related to the mixed criticality work that we're doing for aerospace to try to show the overlap with the Zen efforts. There's a link to that. And you're also welcome to join our calls. So we have an aerospace ELISA call actually tomorrow. Every month we do one of them, and I put a link to how to sign up. And that's how you get involved in that, in working that mixed criticality material. And that is a separate like sign up from the one we just talked about with Ayan and the mailing list for Zen. So we sort of have the two efforts going, working together. So
I don't see any questions in the Q&A, but if you would like to speak, since we still have 10, 12 minutes, raise your hand and I allow you to talk. So you can just directly speak instead of typing. Oh, okay, I see Raphael. Let me see. Okay, I just allow you to talk. So just unmute yourself and speak. Raphael, you have to unmute.
No, thank you. Can
Yeah.
you hear me?
Yes.
Perfect. I worked a while ago for integrating Zephyr and Xen on a Xilinx board for mixed criticality avionics systems for the University of Stuttgart. And I have never made the DOM0 up and running with Xen to pull up multiple different DOM-Us for Zephyr. Has anyone already done something similar already?
Rafael, yes. So we have done some work. So we are able to get, when you say that creating Zephyr DOM-Us from the DOM0 tool stack. So yes, that part is done, and it is supported. It is there. I'm sure if Artem is here in the call, he can give more details about that, because there has been quite a lot of work that's going on the Zephyr to support Zen. Now, you also spoke about a bit about the DOM zero less. So that is like when you don't need a domain, but you can boot Zephyr in parallel with some other domains. So this is the DOM zero less scenario, and that also has been supported. I think what I can do is that after this call, I can point you to at least one of the upstream tests where we are using Zephyr, and maybe you can take a look at it, and then maybe we can see like what's the issue that we are facing here.
Okay, this would be very helpful. Thank you a lot. Yeah.
It's I'll drop a link to where the actual GitLab group is as well, because that material's all out there, right?
Yeah. So this is there.
Yeah.
Yeah. And if you want to see the upstream CI, so it is here in the where is it? It's here in the hardware Zen, and you have the different pipelines that's going on here. So if you click here on any pipeline, so we have quite a lot of tests that are running out there, and yeah.
And they are running on the ZCU board, or they're tested against which hardware explicitly?
Most of them are tested against the QEMU. So they are not tested on a specific hardware board. I believe that we have added support to one of the Xilinx board. I don't remember whether it is ZCU 102 or one of the other boards. Sorry, say again.
ZCU 102, yes.
Yeah, ZCU 102, yes. So maybe I can find that particular job which is running in the upstream, and I can send you the link there.
One thing to add is that anyone can board the CI loop upstreaming then. So anyone can contribute. There are contributors that are adding laptops, for instance, for desktop style testing. But if you have an embedded board that you care about, there are now RISC-V boards. Added. You just need to, you can just power it on in your house and hook it up, and there are ways to.
Any other questions?
Has it been enabled with cache coloring as well? The Zephyr instances? Probably.
Yes. So cache coloring has been like recently upstreamed. There has been work that's going on with cache coloring to run the different domains. Now, I do know of Linux, whether it has been done for Zephyr, because cache coloring is not something that is VM dependent. It is more like Zen is assigning different colors to different VMs. So it is possible. It should be possible to run.
Because I did it against Linux real-time kernels, and I haven't tested it so far against these Zephyr ones, but I think this should work.
Yeah,
but I was not sure if I can assign them dynamically within the runtime.
You cannot change the colors once the VMs are running, but you can start dynamic VMs with different colors.
Very cool.
Meaning with Excel Create.
Yeah, with XL Create, but within from Zephyr SA DOM 0 as well, probably.
Do we have questions from other people?
Artem or Stefano, do you want to take on that? So you're saying that can Zephyr be run as a DOM 0 or not? Is that the question?
Artem, I can allow you to talk. Yes.
Oh, okay. Yeah. So to run, support to run Zephyr in DOM0 is upstream in Zephyr since I think last autumn. So you can actually run Zephyr in DOM0. To control domains, you actually need tool stack, and we are now in progress of adding Xemli as a submodule to the upstream of Zephyr. That is already published, but we need to do some major cleanup prior to do that. Like some folks are really pushing hard just to do that. But yeah, you can actually create, destroy, whatever do with the domains from Zephyr DOM0. Yeah, and cache calling, of course, is supported as well. Cache calling doesn't get Zephyr DOM0.
Very cool. Can I maybe reach out to you, Artem?
Yeah, please. Happy to.
Great. Anyone else? If you need to speak or have a question, just raise your hand and I'll give you the enable you to be able to speak.
There is any interest in the artifact side of stuff, the link to that fuchsia group, you'll see a series of projects in the folder that are where the work in progress on like requirements and some of the design and some of the architecture / config conversations and stuff. The materials out there, there's test example MRs and things with like the mocking approach, the white box mocking stuff. So that works all in the open. This stuff we've all been talking about in this presentation, that's the working space there. So
yeah, maybe I can show one of the merge requests that you have.
So if anyone thinks Boeing isn't doing open source work, we're publishing a lot of stuff. We're trying to figure this stuff out. We're trying to make this stuff work because the scale of what we're trying to tackle here is large, and the work's out there. Love to have people review and give feedback. And there are some advanced test approaches here because you're testing all the perfect scenarios and all the not perfect scenarios. And single functions could have a lot of that, a lot of procedures. So
I mean, if you are interested in this Ceedling-based mechanism, so we had a presentation yesterday by Matt Whitehead, and he explained all of this with using Zen as a reference. So I can point you to that webinar, and yeah, so so these tests you will be able to see there in the open. So these are the test specification, and then here you will see the actual pipeline for the test. Where is it? It's here. Sorry, automation, add Zen page table aerospace test procedure. So this is one of the key features that's getting tested using the Ceedling mechanism.
Ayan, will you be adding that to the meeting wiki list?
Yes, I will. Sorry, I forgot about it. Yeah.
There's a link I just threw in the chat to past recordings and sort of the minutes for those calls. Cool.
I would say that join us at the London workshop and at the Zen Summit in Munich, and we will be having more interesting discussions on all of this, and we can do some whiteboarding together.
When is the Zen Summit in Munich?
It's in Munich. I think it is 15th to 17th September. But if you ping me on the matrix, I can confirm and I can send you the official announcement. I believe it's 15th to 17th September. I think so.
Thanks.
Mm-hmm.
Well, we're at the top of the hour. Thank you very much, Aaron and Matthew, for this talk and facilitating the discussion. I think this is very insightful. Hopefully, attendees got a lot of valuable information. We'll get the slides and recording distributed to registrants, and the recording will also be the recording will also be published on the ELISA YouTube channel. So keep your eyes open for that. And ELISA hosts a number of seminars each year. So if you go to events elisa.tech, you'll get all the upcoming events details as well. So thank you very much for participating, and we look forward to you contributing to ELISA and Zen, Zephyr, Linux, all that, to keep moving things forward. So thank you very much.
Thank you.
Bye.